Hey everybody. So I'm going to review all the key concepts dealing with confidence intervals. So I'm going to try to keep this just a summary video, so not too long, but again, I want to hit the key points and make sure you get a clear explanation. So here's an example problem that we're looking at where we have a survey that was talking about drugs, and it said that 2,312 of the 5,914 of randomly selected full-time U.S. college students were classified as binge drinkers. I think that's 5 or more drinks in a single setting. Calculate and interpret the 99% confidence interval for the population proportion P that are binge drinkers. Okay, so first let's just review and make sure we have a clear understanding of what a confidence interval is. So essentially, a confidence interval the whole idea behind a confidence interval is to make a prediction about something. In this case, you want to predict what percentage or what proportion of college students are binge drinkers. Now, from this sample, we would basically just take the proportion of using these numbers, which is going to be what's called our sample proportion, or p hat. P hat, this is a hat. It may look like a triangle, but it's actually a hat. And this is going to be equal to the 22,312 that said yes, or that were classified as binge drinkers, over the sample size, 5,914. And we'll see what we get. So we have a calculator to do this. 2,312 divided by 5,914, which is about 39%. Wow. 0.39, we'll say. 0.391 to rounded. Now, this is just a survey. So we just understand and know that this is not necessarily going to be equal to the true population proportion of all the binge drinkers that there are in, I guess, all in the US, I guess, because we only surveyed some of them, because we can't survey all of them because this is too much. There's too many to survey. It would take forever. It would take a lot of money, and it's not worth it. By the time we get to the last one, maybe the status of the first one we surveyed changes. So it's impractical to survey everybody. That's why we do statistics, remember? So we want to use this sample data to make a reasonable prediction of the true proportion. So this is going to be our point estimate. We start from here. And this guy is what is going to be the center of our confidence interval. So the center is 0.391. Point estimate. It's this dot. Now, we're going to say it's an interval because we want a range of values, because we don't want to just bet that this is the value, because we're probably not going to, the chances of this being the exact population proportions are low. But if you make a range or an interval of values, your chances are greater. You're more confident that it's going to be in a range of values. Now the question is, how big do we make this range? That's going to depend on how confident we want to be. The higher the confidence, the bigger the range, because if you want to be 100% confident, you can make this infinity, or 0 to 1, because all proportions are between 0 and 1. But that's not going to be useful. Now, depending on what type of data you're studying and the importance of being accurate, we're going to have a higher confidence interval for like medical studies, cases that involve death and serious health consequences. If it's like business where you could just lose some money, maybe lower, 90%. We picked 99%. So this interval will still be centered at 0.39, and it's going to go to the right some amount, which we call the margin of error. Margin of error, which is ME for short. That's not how you spell it. I'm going to write ME because you should remember this. M.E. This far. But also, since this is the center, we're going to go that same length to the left, below. So ME is also this length, just in the negative direction. And let's actually use this tail thing for that. So our interval is going to be the point estimate plus and minus the margin of error, above and below. Now, how do we get the margin of error? Well, that's going to be based on our statistic, or on our statistic and our standard deviation from the sample data. So what we have is our margin of error will be equal to our critical value times our standard deviation of the statistic, or standard deviation, which is SD. The critical value is basically just how many standard deviations away we want to be. How many standard deviations away is 99%, is a 99% confidence interval. Now, let's refer back to the early chapters where we first learned about normal curve, because it's all based off of this. Because we're making these calculations based on that the idea and the belief that the distribution is roughly normal, meaning that it's centered at the mean, or if it's standardized 0, and if we try to capture 99% of this curve, we could use this normal curve to figure out how many standard deviations or what the z-score, critical value, would be in this case. So you want to see what is the z-star, or critical value, in this direction. It's the opposite in the left, because getting that z-star is going to tell us what the critical value is. And then we pretty much have the information we need, and we can make our confidence interval. Because if, again, just using the basics, if it was a 95% confidence interval, 95, this part, let's say 95. We know that's about 2 standard deviations away. We should have that memorized. Technically, it's 1.96, but about 2. So we would just put 2 there. We don't expect everyone to have every value memorized, because that's stupid. It's a waste of time. But we're going to look at a table or use a calculator to figure it out. I'm going to use my good old calculator. So remember, calculate the normal distribution area to the left. Normal CDF. Area to the left of 99% is 0.5%. So we have inverse norm, 0.005. Or 0.005. And we're going to get negative 2.57 and positive 2.57. So 2.57 standard deviations away is our critical value, or our z-star. And to find our standard deviation, we're going to use the equation, or the formula given to you in your formula sheet. That is going to be the square root of p hat times 1 minus p hat, all over the sample size. In this case, our p hat is the 0.391. 1 minus 0.391 divided by n, which is going to be 5,914. So just showing you the values explicitly. 0.391 times 1 minus 0.391 over 5,914, all square rooted. So let's calculate that. Got my red marker, 0.391 divided by 5,914. And we get the square root of 4-ish, 4.00-ish, the negative. Finally, we get 0.006. Let me double check that, because that looks interesting. No, that's correct. So then, B. Let me use the red again. 0.0063-ish, 0.0064-ish. So we use this as our margin of error. So our confidence interval is going to be our point estimate plus or minus that. So we'll have 0.391 plus minus 0.006 plus minus 0.00634-ish. This number. Or no, sorry. that times 2.57, which times 2.57. So this number, 0.00634 times 2.57 will be 0.016, about 1.6%. Gotta get down low, 0.0163. This is our comments interval. When it says plus minus, that means on one side we add this. So 0.391 plus that. So the right upper bound will be 0.4073-ish. The other one, we do 0.391 minus that. 0.391 minus 0.016. And we'll get 0.3746. 0.3746. This looks messy. I got to do a better job of writing that. An eraser at. There we go. 0.3746. All right. So our comments interval is this set of values, 0.3746 to 0.4073. So about 37.5% to 40.7% is what we think the true population proportion will be in. So again, this is better than just guessing a single value, because we're going to be very confident, or 99% confident, that the population proportion will be in there because we have a good amount of data. We have 5,914 data points. Now, again, doesn't mean that it's going to be in here for sure. It just means that if we use the statistical method where we took a random sample of this size and calculated all of this, about 99% of the times we would get confidence intervals that would actually contain the true population proportion. We don't know which of those confidence intervals would have it, but on average we would have, if we made like millions and millions of confidence intervals, which we wouldn't, because what's the point of that? If we made a lot of confidence intervals, about 99% would have the value, the true population proportion in it, and we call it the population parameter in general. So that's the basic idea. So make sure you know that, because this chapter is actually pretty simple once you understand this basic principle. The other parts of this chapter are just little add-ons to this, like what type of sampling how would sampling methods affect this? Like this doesn't, when it comes to like non-response surveys and stuff, this doesn't take care of that, because it's simply a math process. Now let's finish off and just look at how we calculate the confidence interval for population mean. So I'm going to time travel here, so just hang on. All right, so now let's look at a scenario where we have to calculate a confidence interval for sample mean. So here we got an IQ test taken by simple random samples of 60 of the over 1,000 students at a school, and then we get a sample mean of 114.98. So a sample mean will be X bar, which is what we use X bar for sample mean, 114.98, and the standard deviation of the sample is S sub X, about 14.8. So if we want to construct a confidence interval for estimating this sample, or estimate the population mean, we use the same principle as we did with population proportion. We start from here. We center our confidence interval at this value. So we have the sample mean, or point estimate, plus minus our margin of error, just like before. Now our sample mean is X bar, because we're talking about means from a sample. Now how we get the margin of error is we're going to use a critical value, not T star. We're going to use not Z star. We're going to use T star, because the distributions won't necessarily be approximately normal if the sample size is small. Once they get big, the t-distribution pretty much matches the z-distribution. But the key thing to know is, and to pay attention to, is that you're going to need to use t star for your critical value. And the formula for standard deviation will be, I believe, the sample standard deviation over the square root of n. Now, I should mention one thing, which is not really a big deal, but some teachers make a big deal. Just I don't know why, just to be annoying. But this is not really called the standard deviation. They call it the standard error. Standard error. Because it's just something else to call it. Because if you call it standard deviation, it would be wrong. That's really the main reason. Don't overthink it. It's still the same principle as a standard deviation. It's just that this is going to be instead an estimate of the true standard deviation, because the true standard deviation, we would need every single value in the population. But if we had every single value in the population, we wouldn't even be doing this confidence interval, because we could figure out the true mean of the population. So then we wouldn't give a crap about this standard deviation at all. So it just takes care of itself. So just don't overthink it. This is just the same principle as standard deviation. It's just a standard deviation of the sample. So that's just the formula we use, and that's pretty much all you have to know. And just t star is the critical value, and we use it just like we use a z star, except we look at sample. Well, I guess that is different. We look at sample size or degrees of freedom. Let me actually write that. So degrees of freedom will be determined by our sample size, which is going to be 1 less than n. Our degrees of freedom would be n minus 1 purpley, and that will be 59. So you can look at my other videos to get a clear breakdown of how we find that in our table. For now, I'm just going to show you through the camera really quickly, because it's just review. Remember this table in the back of our book? Oh yeah. And we look at the t-table. The t-table on the left side has the degrees of freedom, and conveniently, where's the pen? We can look at the confidence interval down here, 99%. So we look for where it has 59 or less, which is 50. So we go to the value that's less for degrees of freedom if it doesn't include it. Since it doesn't include 50 and 59, we go to 50. And that will give us a t-star of 2.678. So t-star 2.678. If you use a calculator, this is actually much more precise, but you don't have to. And again, don't worry about being super accurate, or you're accurate, or you're rounding, because the answers on the actual exam won't be due to rounding. You'll have a clear answer. They make them very distinct, so that rounding differently won't cause you to answer wrong. So then we just do the math. So we get 114.98 plus minus 2.678 times 14.8 over the square root of 60. And times 2.678. 5.11677. So we get, let me go over here and I'm going to lean down here. 114.98 plus minus 5.11678. So again, we add and then subtract from here. So lower bound, subtracting this from that. Minus 5.1167. 109.86 for the lower bound, 109.86. And the upper bound will be 120.096. So we then formally say that we are. Oh, I didn't even write the confidence interval. I didn't tell you what the problems say. I think it said. Oh, 99%. Yeah, we look at 99%. Duh. We are 99%. We are 99% confident that the true population mean X bar of IQ scores of this school, of the students at the school, is somewhere in the interval of 109.86 to 120.096. So again, that means that if we were to make many thousands of these confidence intervals using the same method, about 99% of them will capture the true population mean. So there you go. I hope that helps. Let me know if you have any questions. Please make sure you tell your friends and tell your buddies, and let me know if you like this video. And make sure you subscribe and like, and tell everybody, and say bye to Pepe because it was a lonely day. Bye guys. All right. Thanks a lot, guys. Catch you in the next one.